Hi everyone. In today's Fundamental Skill Builder series on the subject of organic chemistry, I'll be teaching you on drawing the Lewis dot structure of a molecule. To walk this through, let's look at an example. Draw the Lewis dot structure of CH2O. This molecule is known as formaldehyde. So there are 4 discrete steps when drawing a Lewis dot structure of a molecule. First, we're going to determine the number of valence electrons for each atom, and we're going to add up the total number of valence electrons for the whole molecule. Next, we're going to connect any atoms that form more than one bond. Hydrogen atoms only form one bond each, so we'll save those for last. In this case, we're going to connect the carbon and the oxygen. Next, we're going to connect all of the hydrogen atoms. We place the hydrogen atoms next to carbon because carbon has more unpaired electrons than oxygen. And finally, we're going to check to see if each atom, except hydrogen, has a full octet. In our case here, neither the carbon nor the oxygen has a full octet, so we're going to pair up the unpaired electrons as a shared double bond between the carbon and the oxygen. So now all of the atoms have achieved the full octet. As a general rule, when drawing Lewis dot structures, remember that you simply cannot add more electrons to the drawing than the total number of valence electrons in the molecule. For each atom to achieve an octet, the existing electrons must be shared. In this case, the total number of valence electrons should be correct when you're finished. In our example, we have 1 carbon atom, 2 hydrogen atoms, and 1 oxygen atom, giving a total of 12 valence electrons. And in our drawing, we also have 12 valence electrons, so they're in agreement. And for today's exercise, draw a Lewis dot structure for each of the following compounds: C2H6, C2H4, C2H2, C3H8, C3H6, and CH3OH. In C2H6, this molecule is called ethane. We have 2 carbons and 6 hydrogens. Therefore, we're going to have 2 times 4 plus 6 times 1 for a total of 8 plus 6 of 14 valence electrons total. We're going to start with combining the carbons each, and then we're going to add in the hydrogens. After we finished, we realized that both of the carbons have achieved the full octet, and if we count the total number of valence electrons and compare it with the total given by the molecular formula, we have 7 bonds here times 2 should be 14 and matches up, so we're finished. In C2H4, this molecule is known as ethene, whereas organometallic chemists call it ethylene. C2H4 has 2 carbons and 4 hydrogens. So we have 2 times 4 plus 4 times 1, a total of 8 plus 4 of 12 valence electrons total. We're going to start out by connecting the carbons, and then connecting the hydrogens to the carbons. After we finish connecting the 4 hydrogens, we see that both of the carbons do not have a full octet, so we're going to add 1 extra bond. So now both of the carbons have a full octet. And if we count the number of bonds in this molecule, there's 6 times 2, which is 12 electrons, matches up with the molecular formula, so we're finished. In C2H2, this molecule is known as ethine, whereas organometallic chemists like to call acetylene. We have 2 carbons and 2 hydrogens for a total of 2 times 4 plus 2 times 1 of 8 plus 2 of 10 valence electrons. As always, first connect the carbons, then connect the hydrogens. We see that the carbons do not have achieved full octet, and in order to do so, we need to add a triple bond between the carbon. And now both of the carbons have a 4 octets. And if we count the total number of bonds, we have 5 times 2, which is 10 electrons. This matches up with the total number given by the molecular formula, and so we're finished. C3H8, this molecule is known as propane. In C3H8, we have 3 carbons and 8 hydrogens, for a total of 3 times 4 plus 8 times 1 of 12 plus 8 of 20 valence electrons. We're going to connect the carbons first, then we're going to add in the hydrogens. We see that all 3 carbons have 4 octets, and if we count the number of bonds, there's 10 total bonds, and 10 times 2 is 20, which matches up with by total number of valence electrons given by the molecular formula. So we're finished. C3H6. So there are actually 2 different compounds that have formula of C3H6, but I'll only show you the linear one. If you can figure out what's the other one, feel free to comment in the video below. This is known as propane. In C3H6, we have 3 carbons and 6 hydrogens, for 3 times 4 plus 6 times 1 of 12 plus 6 of 18 valence electrons total. We're going to first connect the carbons, but in this case, watch out, we can only have 6 hydrogens, so it will look like this. But the middle carbon and the right carbon don't have a 4 octet, so we're going to add a double bond there. So you can also draw it like this as well, which is perfectly the same thing as the one above. And we see that there's a total number of 9 bonds, and 9 times 2 is 18, which matches up with the molecular formula's total number of valence electrons, so we're finished. In our last molecule, CH3OH, this molecule is known as methanol. In CH3OH, we have 1 carbon plus 1 oxygen plus 4 hydrogens. So we have 4 plus 6 plus 4 times 1 for a total of 14 valence electrons. So we're going to connect the carbon and the oxygen first. Next, we're going to connect the hydrogens. So carbon generally likes to have the hydrogens, but we still need 1 more, and we're going to connect it to the oxygen. And remember, the oxygen generally likes to form 2 bonds to have a net charge of 0. And so if we count the total number of bonds, we have 5, which is 5 times 2, which is 10. 10 plus 4 lone pair electrons, which gives a total of 14. And this matches up with the molecular formulas of 14 total valence electrons, and so we're finished. So on your own, try these 2 exercises. Borane, BH3, is very unstable and quite reactive. Draw a Lewis dot structure of borane and explain the source of the instability. There are 4 constitutional isomers with the molecular formula C3H9N. Constitutional isomers are essentially compounds with different rearrangements of the atoms, but the same number of total valence electrons in atoms. Draw a Lewis dot structure for each isomer, and determine the number of lone pairs on the nitrogen atom for each case. So feel free to pause the video for a couple minutes and then hit play and see if you get the same answer as I did. So once you're finished, here we are with BH3. This is boron. It just has a single central boron atom with 3 hydrogens attached, and there's no other lone pair electrons or single radical electron on boron. And the reason why boron is very reactive is that it has an incomplete octet. In general, any substances that has incomplete octet, we'll see in actually when we do reactions of organic chemistry on the alkenes, there's a compound that uses BH3, boron, and is a very reactive reagent. So as with always, any compounds that have incomplete octet are going to be unstable and reactive. In the second semester series of organic chemistry, there's a commonly used salt called aluminum chloride, and also has incomplete octet, and is very reactive in the type of reactions for the aromatic compound. I'm not going to discuss it, but feel free to find out if you want to ask me. Now C3H9N, there are 4 different constitutional isomers with this formula. As you can see, if you drew all of these 4, then you get them right. And as well, we found out that in each of these 4 structures, the nitrogen atom has only 1 lone pair, or 2 lone pair electrons. So this is the answer for this question. And if you want more practice, here are some extra questions. And as always, feel free to email me with questions and suggestions. And I hope today's series on drawing Lewis dot structure of a molecule helped for building the fundamental skill builders in organic chemistry. Thank you.